Let's talk about solving homogeneous linear systems with constant coefficients. For the linear system, dx dt equals negative x plus y, dy dt equals 7x plus 5y, find the eigenvalues and corresponding eigenvectors, sketch the direction field, and find the general solution. You may wonder, why are we finding eigenvalues and eigenvectors? What does that have to do with the general solution? You'll find out in a moment. If we let x equals x1, x2, and let A equal this matrix, negative 1, 1, 7, 5. I think you can see where that's coming from, right over here. Sorry, need the pen. Yeah, so you can see where that's coming from right over here. Then we can write this as dx1 dt, dx2 dt equals negative 1, 1, 7, 5 times x1, x2. In other words, dx dt equals ax, or x prime equals ax. The characteristic polynomial of A equals negative 1, 1, 7, 5 is lambda squared minus 4 lambda minus 12 equals 0. If you factor it, you find the eigenvalues are lambda equals 6 and lambda equals negative 2. And the corresponding eigenvectors are 1, negative 7 and 1, negative 1. You can find these using Wolfram Alpha or Mathematica or a TI Inspire, or you can just do that by hand. The direction field, slope field, looks like this. You can use any direction field or slope field plotter to generate this. So again, these are what the general solutions to the system are going to look like. But we wanted to find a solution algebraically, not just some graph. So here's how we do that. Suppose the n by n matrix A has n linearly independent eigenvectors, v1, v2, blah, 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 v sub n, with corresponding eigenvalues, lambda 1, lambda 2, blah, 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 lambda sub n. Then the linear system dx dt equals ax has e to the lambda 1t, v1, e to the lambda 2t, v2, blah, 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 e to the lambda sub n t, v sub n, as a fundamental solution set, so that the general solution to this system of differential equations is x equals c1 e to the lambda 1t, v1, plus c2 e to the lambda 2t, v2, plus blah, 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 plus c sub n e to the lambda sub n t, v sub n. In other words, this is a formula for the general solution to a linear system with constant coefficients. Let's apply it. If the eigenvalues of A are distinct, then the eigenvectors are linearly independent. This really helps out because then, notice, this formula depends on the eigenvectors being linearly independent. So as long as your eigenvalues are distinct, you know your eigenvectors are going to be linearly independent. If they're repeated eigenvalues, in other words, if the eigenvalues are not distinct, then the eigenvectors might not be linearly independent. We're not going to cover that in this video, though. So again, here's the general solution of the system. Thus, the general solution for the system we were given is going to look like this. Okay, lambda 1, first eigenvalue is 6, so we plug in 6 there. First eigenvector is negative 7. Second eigenvalue is negative 2. Second eigenvector corresponding to that is 1, negative 1. So this is going to be our general solution. If you don't like writing it like that, you can write it like this. So x1 is c1 e to the 6t plus c2 e to the negative 2t. x2 is negative 7 c1 e to the 6t minus c2 e to the negative 2t. And if you were to graph that for different values of c1 and c2, this is what you'd end up with. You'd get a direction field that looks like that. For the linear system, dx dt equals 3x minus 2y, dy dt equals x plus y. Find the general solution. So we find the eigenvalues for this matrix, 3, negative 2, 1, 1. You know the drill. You know what to do. Determinant of A minus lambda I equals 0. Multiply it out. Simplify. Get this. Lambda squared minus 4 lambda plus 5 equals 0. And that doesn't appear to factor. By the quadratic formula, the solution is going to be blah, 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 blah. Holy cow. 4 plus the square root of negative 4 over 2. I learned about complex numbers when my 8th grade algebra teacher taught me about them. Hey, we can finally use them. That's 4 plus or minus 2i all over 2. In other words, 2 plus or minus i. So the eigenvalues are lambda equals 2 plus i and lambda equals 2 minus i. You can use the techniques we've used before to find the eigenvectors. Again, Mathematica, Wolfram Alpha, or it would be easier, but you can, again, do it algebraically, grind it up by hand. We find that the corresponding eigenvectors for this matrix are 1 plus i, 1, and 1 minus i, 1. So here's what our solution is going to look like. X of t is going to look like this using the formula from before. So in other words, it's k1 e to the 2 plus it times this eigenvector plus k2 times e to the 2 minus it times this eigenvector. Holy cow, I don't want to have i's running around in it because this would force k1 and k2 to be complex numbers, way too complex, pardon the pun. There's a way we can write this solely in terms of real numbers. Let alpha plus beta I be lambda. Let that be our complex eigenvalue for the system with corresponding eigenvector v. The general solution to the system will be, and again, this is cool, this is just in terms of real numbers, k1 e to the alpha t times the real part of v cosine beta t minus the imaginary part of v sine beta t plus k2 e to the alpha t times the imaginary part of v cosine beta t plus the real part of v sine beta t. You'll see in a moment how we use this. Okay, so here's that hairy formula I just gave you a moment ago. So the eigenvalue is lambda equals a plus alpha plus beta I. In other words, that's 2 plus I. So we can see that alpha equals 2 and beta equals 1. So we just plug those into the formula, alpha equals 2, beta equals 1. The eigenvector v equals 1 plus I. The real part of v is just going to be 1, 1. And the imaginary part of v is going to be 1, 0. So we plug those in wherever we see the real part of v. Okay, like that. And the imaginary part of v, just plug that in there. And then we end up with this, okay? X of t is going to be c1 e to the 2t times the vector 1, 1 cosine t minus 1, 0 sine t plus c2 times e to the 2t times the vector 1, 0 cosine t plus 1, 1 sine t. And again, if you wanted to simplify that and write that it's x1 of t and x2 of t, you could just break it up like this. So that's what we end up with. Cool! So complex numbers finally have an application. Awesome.